All right, my friends, section 11.1 is an introduction to limits. So just a little bit about chapter 11. Chapter 11 in your pre-calculus textbook gives a bit of a survey of what's to come in calculus. And it does it, for the most part, from a conceptual perspective. So really, once you start chapter 11, you've started calculus. Anyway, also, just kind of a funny story. Your pre-calculus textbook is called Pre-Calculus with Limits. And the limit piece is referring to the beginning of the introduction to calculus. I used to teach at a private school, and we offered regular pre-calculus and honors pre-calculus. And the regular pre-calculus book had a super cool pink pre-calculus book, and it was just called Pre-Calculus. And then the honors pre-calculus class had an orange book like yours that said Pre-Calculus with Limits. And I had a student in the non-honors pre-calculus who would tease his friends about how his class didn't have limits like their class did. Anyway, just super funny. Not super funny at all. Mildly funny, at least. Anyway, let's get to business, my friends. So warm up for you. Let's have you graph f of x equals x squared plus 2x minus 8 over 2 times the quantity x minus 2. All right, my friends, super good time to pause the video and see if you can remember how to do something like that. Pretty important that you toy with that and poke it with a stick just a little bit. So assuming that you've done that, let's go ahead and analyze this thing. This is called a rational function because it has a polynomial divided by another one. In analyzing it, the first thing that you should always do is factor it down as much as possible. The denominator is factored down as much as possible. And so let's factor the top. And what do we notice when we get this factored? We notice that the x minus 2's cancel out. And why do they cancel out? Because if x was anything but 2, then you'd have, let's say x was, 25. Then you'd have 25 minus 2, and then this would also say 25 minus 2. So you have 23 divided by 23. So the reason they cancel is because for any number except for when x is 2, these numbers would divide out. And what if x was 2? If x was 2, you'd have 2 minus 2 down here, which is 0, times 2, so you'd be dividing by 0. And then you'd also have 0 times, 6, I guess, if x was 2. And so you'd have 0 divided by 0, which is considered an indeterminate form, and it's definitely undefined. So the point is this, this big messy fraction is exactly equivalent to x plus 4 over 2 for everything except for when x is 2. So I'll just go ahead and say this. Okay, so now let's look at graphing this. Now that you can kind of see you don't have a rational function anymore, you can divide the 2 in, and you've got 1/2 x plus 2. And so how adorable is that? You basically had something that looked like it was going to be a big, scary rational function, but it's just a cute little line graph with a hole at 2. So I think I'll put it over here. Okay, y-intercept of 2, up 1 over 2, I'll put a hole there, up 1 over 2, down 1 to the left 2, down 1 to the left 2 again. Mr. Chase would be horrified to see that I draw lines without a straight edge. I'm sure some of you are also horrified. Okay, anyway, so, okay. And then how could I figure out the exact coordinates of where that hole is? I could, look at my picture, go up 1 over 2 from this point right here. Or I could actually plug 2 in to this function right here, and then I'd figure out that hole or removable discontinuity would be at the point 2, 3. All right, my friends. So this is hopefully feels like some review. Now we're going to talk about what a limit value is, and we're not going to do this from a crazy formal perspective. We're just going to do this informally, and then we're going to talk about different ways to evaluate the limits, and that's pretty much what this section is all about. So first of all, let's talk about what a limit value is and notation for it. So I'm going to go ahead and write the notation for it. So let's say you were asked we'll make this example 1. Let's see. Let's ask you to evaluate, and then, so I'm going to write this in print for the first time. So LIM is short for the limit, and then as x approaches 2 of x squared plus 2x minus 8 over 2 times the quantity x minus 2. Okay, so let's talk about this just a little bit. If we were all together in the same room, I would make you read that out loud with me. And so I'm actually going to pretend you're here, and feel free to embarrass yourself and go along with me. Anyway, so when you read this, let's make sure you sound educated, even if you have no idea where I'm going with this. So when you read this, you say the limit. Your turn. Good. As x approaches 2, your turn. Good. Of x squared plus 2x minus 8 divided by 2 times the quantity x minus 2. Okay, so you just want to make sure you can read this part. I'm a firm believer if you sound educated, it's easy to be educated. Okay, so now let's talk about different ways to do this. So we'll have, let's see, using each method. Okay, let's talk about the graphing method. So graphing, let's see, evaluating it, we'll say graphically. Okay, so if you're doing this graphically, then you would actually either by hand, like we just did, or maybe with a calculator, you would graph the given function rule. So you would just do exactly what we did there. Now, it's a matter of understanding what they mean when they say limit as x approaches 2. When they say this, they're not talking about what happens when x is 2. I repeat, they're not talking about what happens when x is 2. We already have notation for that. That's f of 2. So they're talking about what happens when x is a number infinitely close to 2. So they're talking about what if x is like 2.0000001, or what if x is 1.9999999, okay?
Mommy, did you eat carrot cookies?
I think I ate 1 carrot cookie. Yes. But I have to do this video, Tweety, okay?
Mom ate 1 carrot cookie. So that means 1 more left.
I just got busted. Okay, anyway, so we're not talking about what happens right at 2. We're talking about infinitely close to 2, above it and below it. What happens when you plug those numbers in? And so what happens when you do plug those numbers in? Well, you get y values. If you look at the picture, you would get y values that are getting closer and closer to 3. The closer and closer the number that you plug in gets to 2, the closer and closer the y values would be to 3. So we would say that the limit as x approaches 2 of this expression, according to the graph, is 3. Even though the number 3 never really got attained, you are getting infinitely close to the number 3 as you get infinitely close to plugging 2 in. So we would say, graphically, Oh, by the way, this is what my LIM looks like pretty much from here on out. So you just have to know that that is the limit. So we would say the limit as x approaches 2 of x squared plus 2x minus 8 over 2 times the quantity x minus 2. We would say that that is 3. And again, it's because we're talking about what happens if you were to evaluate the rule at numbers infinitely close to 2, but not 2. And then what are your answers getting infinitely close to? And we would say that you're getting closer and closer to 3. Okay, I hope that makes sense. If it doesn't, as we go through the lesson, we'll try to fine tune it for you. Okay, another way to evaluate this, and if what I just said here does not make sense, this is probably going to help. Another way to do this is to do this, it's called, what is it called? Numerically. Numerically. Okay. Now, another, in my opinion, whenever they say numerically, they're basically talking about a table of values. So I'll just say AKA, table of values. Okay, so if you're trying to get the same answer, the same information, but doing it instead of having to bother graphing it, and boy oh boy, is it easy to imagine times when you don't want to graph things. So you might fall back on a table of values instead. And then I'm also grab your calculator. If it's, pause the video, go get your calculator, get it nice and ready because we're going to use it for this because we just don't have time to not use our calculator for this, okay? So here's what we're going to do. We're going to make a t-table, and we are going to plug in strategically chosen x values into our function rule, where this is our function rule. And so to get ready for that, grab your calculator, blow your dust and possibly cat hair off of it. Anyway, and here's what we're going to do. We're going to go to y equals, clear anything out that you've got, and let's enter this function rule in parentheses, x squared plus 2x minus 8. Oh boy, 2x. There we go. Minus 8 divided by, let's see, 2 times x minus 2. Wow. Okay. Wow. X minus 2. Good night. Okay. It'll be a miracle if this graphs the way I want it to. But anyway, check your window. I've got, like, for example, 0 to 300 from a previous problem. So I'm going to go ahead and reset this. So I'm going to do zoom. Where is it? Zoom standard. There it is. Number 6 is zoom standard. That just kind of puts things back at -10 to 10. And -10 to 10. Oh, you know what's funny is I don't need a window anyway because that's not what I'm doing. I apologize. Oh, hey, here's the graph that we got, by the way. Notice it doesn't look like there's a hole at 2 because how big is the hole? Oh, that's right. It's infinitely small. But if you were to go to calculate, since we're here, we're just going to calculate and then go, let's see, calculate value and then put a 2 in. Then notice that it'll say when x is 2, I don't know what y is, because there is an infinitely small hole when x is 2. Okay, but that was totally a detour. Sorry about that. So let's see. Let's go to, instead of graphing, the point is to do a table. Dun, dun, dun. Okay, let's see, clear. Oh, well, I've got old stuff in there. Ignore that. Anyway, so if we're going to make a table of values, let's talk about strategically choosing x values to demonstrate what a limit is. So we're going to do... we're going to talk about what happens when you approach like 2, for example, from the left. So start by thinking of what's a number that's really close to 2, but just a little bit to the left of 2 on the number line. I would say maybe 1.9. And then to demonstrate approaching 2 from the left side, we're going to add 1.99 and getting even closer, 1.999. Like creeper close. And so this is demonstrating what happens as x approaches 2 from the left side. So using your calculator, to make sure that you've got the setting right, if it's not going to be nice to you like mine's about to be, you could always go to table set right here. It's the, oopsie, the F2 key. Table set. Make sure that it is going to ask you for the independent variable but then automatically calculate the dependent variable. That's the setting that you want there. Okay, so then let's type in 1.9 and then it'll tell you the y value. 1.99 getting closer to 2 from the left, 1.999 getting closer to 2 from the left. And so you can see on the table that the closer you get to 2 from the left, what's happening with the y values? They're getting closer and closer to 3. There you go. So you could kind of fill those values in. So we got 2.95, 2.995, 2.9995. Okay. Now, what have we just demonstrated? And I'm going to use some notation that you'll need to be comfortable with. So in these rows right here, we demonstrated that the limit as x approaches, watch this, 2 from the left, that little superscript minus sign means from the left of x squared plus 2x minus 8 over 2 times the quantity x minus 3. We showed that that is approaching the number of 3, since as you got closer to 2 from the left, your numbers got closer to 3. I hope it makes sense that whatever you get from a numerical method should tell you the exact same thing that you get from a graphing method, since after all graphs is points that you get when you plug x's in and get y's out. Okay, now let's say we use the same table, and let's demonstrate what it looks like when you approach to from the right side. So let's say your approach, I'll put 2 here, and then we're just gonna say like error, or like leave it blank or something, because your calculator wouldn't know how to plug 2 into this function rule. Oh, if I copy it right, sorry, that 3 should be a 2. My goodness, I'm having a hard time focusing. Okay, so let's plug in numbers really close to 2, but from the right side. So here's how I'm gonna do it. I'm gonna do 2.1, because that's pretty close to 2 on the right side. And I'm gonna get a little closer to 2, and a little closer to 2, like creeper close. And then you can enter these in on your calculator. So you can do 2.1, 2.01, 2.0001. Add a couple extra, add a couple extra zeros if you want, whatever. Anyway, and then you can see the y values, whoops, if I put them on the screen, you can see the y values are getting closer and closer to 3 the closer you get to 2. So I'm gonna put it like this. There we go. And what did we demonstrate in the bottom 3 rows? We demonstrated that the limit as x approaches 2 from the right of this expression, x squared plus 2x minus 8 over 2 times the quantity x minus 2, we demonstrated that that is also 3. So by the definition of limit, and listen carefully to this, your double-sided limit, in which we had here, where you don't see any superscript on your target number, here your target number was 2. If you don't see any superscript on your target number, it's considered a double-sided limit. By definition, a double-sided limit only exists if the left-sided and the right-sided limit values at that target number both exist and both equal the same thing. So we would conclude, based on this information, that the limit as x approaches 2 of x squared plus 2x minus 8 over 2 times the quantity x minus 2 is indeed equal to 3. All right, my friends. So this lesson is just about understanding what limits are, that they're different than function values, because we're not talking about what happens right at the target number. We're talking about what happens when you get infinitely close to it. And then you're supposed to be able to demonstrate finding limit values either graphically or numerically, or sometimes side by side, just to show that you understand that they do give you the same thing. All right, my friends. Let's look at another example, example 2. let's say I give you, okay, let's say I give you a piecewise defined function. F of x equals, and let's actually give you, okay, let's give you the absolute value of x minus 2 plus 3 for everything but x equaling 1. And then we'll say, let's say, we'll make it be 2 when x is 1. Okay. So I'm going to tell you right now that if something is easy to graph like this, then I would recommend the graphing approach. I'm not a big fan of t-tables, even if I can use my calculator. And that's part of the reason you've had so much graphical training, is so that this is the kind of thing that at some point, once you get used to it, you could just do it in your head, in your mind's eye. For now, I keep making you do it on paper, and I'm sure it's annoying. But at some point, probably next year in calculus, you kind of get to do things like this in your head if you'd like. And so we're just kind of practicing that to make sure you're ready. So let's just go ahead and graph this. So part A, I'll just make it official. Let's graph it. Okay, so absolute value graph got shifted to the right 2 up 3. Then to the right and left 1, and then up 1, to the right and left 2, and up 2. Okay, so this is what this first piece would look like if it wasn't for the domain restriction. But they said that you're supposed to have it look like this graph, except at +1. So that means at +1, it would never actually attain the point 1,4. So you'd have a removable discontinuity or a hole right there. But according to this piecewise defined function, your function value should be 2 when x is 1. So when x is 1, you'd actually have a function value of 2. Funny story, one name for this type of discontinuity that you have here at +1 is a hiccup discontinuity, because you're going along, and then there you go. All right. Hopefully that just made your day great. All right, part B. Let's see. For part B, let's say I ask you to evaluate each limit. So first, let's ask you, what's the limit as x approaches 1 from the left of this function? And then what's the limit as x approaches 1 from the right of this function? Oh, when I say, 1. Yeah. And then what's the limit as x approaches 1 of this function? And then last question, what would you say f of 1 is? All right, my friends, go ahead and take a second and see what your answers are. It's very important that you think this through on your own before you just let me give you the answers. So I'll give you a second. Okay, that was definitely more than a second, but limit as x approaches 1 from the left. So here's 1, and we're approaching 1 from the left. We're getting infinitely close, like we're plugging in the 0.99999 stuff, but we're not plugging 1 in. So I claim that you would actually get a number that gets closer and closer to 4. And so we would say the left-sided limit here is 4. Limit as x approaches 1 from the right. So this time we're approaching positive 1, but from the right side. So we're not plugging 1 in. I repeat, we're not plugging 1 in. We're plugging in 1.00000001. And so when you plug in numbers that get infinitely close to 1 from the right side, you get numbers that get infinitely close to 4. So we would say the limit as x approaches 1 from the right of this function is 4. So since the left-sided limit and right-sided limits at 1 are both defined and both equal 4, that would mean the double-sided limit as x approaches 1 of this function is also 4. Now, what is f of 1? Well, if you plug 1 in, you'd get 2. So f of 1 is 2. So I'm hoping that this example helps you to see the difference between a function value at a target number and a limit value at the same target number. They are not necessarily the same thing. All right. Now, before we move on, just to make sure that I'm thorough here, what if I was to change the target number but ask you about the same picture here? Like, what if I was to ask you, what's the limit as x approaches, we'll say 3 of this function? And what is f of 3 of this function? So let's look at the double-sided limit as x approaches 3 here. So as you approach 3 from the left, you would get 4. As you approach 3 from the right, you would also get 4. So we'd say the double-sided limit is 4. Since the left and right-sided limits at 3, we're both 4. Now what's f of 3? F of 3 is also 4. So notice that sometimes your function value and your limit value at a certain target number are the same thing, and then sometimes they're not. So think about, what would that mean about your graph if your function value and your limit value are the same thing? And what would it mean about your graph at your target number if they're not? So if your function value equals your limit value, then that means that your graph is continuous there. It's that simple. And if your limit value and your function value are two different things, it means you have some type of a discontinuity there. Hopefully that makes sense. All right, example 3. Let's see, part A, let's have you graph f of x equals 1 over x squared. And then once you're done with that, for part B, we'll have you evaluate each limit. Let's get a graph set here. You'll notice I will do most of this work graphically. Our group, we are fairly well trained when it comes to graphing, so it's a strength. So I'll probably have you lean on that. When you get to calculus, it's just so much easier to teach concepts to people that are strong when it comes to graphing than it is to work with a group of folks who are not very strong when it comes to graphing. Now, I'll tell you, I can get just about anybody through calculus, whether you're good at graphing or not, but it's just a lot easier if you are good at graphing. All right, my friends, so in this case, f of x is 1 over x squared. Let's go ahead and imagine that. So if you plug in either 1 or negative 1 for x, you'll get 1 out, whether you're plugging in 1 or negative 1. If you plug in 2 or negative 2 for x, you're going to get 1/4 out. If you plug in 3 or negative 3, you're going to get 1/9 out. If you plug in 1/2 or negative 1/2, you'll get 4 out. If you were to plug in 1/3 or negative 1/3, you'd get 1/9 out, or sorry, 9 out, and that's what I would say arrows are for. So the graph of 1 over x squared has a vertical asymptote at 0, which is why all of your limit expressions are asking about the target number of 0, because that's kind of the most interesting place to start asking questions about for this graph. Okay, so evaluating each limit. Limit as x approaches 0 from the left of this function. There are two ways to answer this. There are kind of two camps when it comes to mathematicians. And if you want, you could find two people from the two camps and then get them to argue with each other until it turns into a big nerdy math fight. But I'm from the camp that says that the limit as x approaches 0 from the left is positive infinity. Now, the authors of your textbook, whom I have a ton of admiration for, disagree with me on this issue, and they would say that the limit does not exist. And here's why they're saying that. They think that since you can never attain the value infinity, that in a way your limit would not exist. So when you check your answer in the back of the book, they're going to say does not exist. I want you to say infinity. How come? Because when you're in Calc BC, you're going to need to know whether you get infinity or negative infinity in situations like this, and just saying does not exist just won't cut it. So I would prefer this answer. Just know, heads up, when you check your answers in the back, they'll say does not exist. Okay, limit as x approaches 0 from the right of this function. So as you approach 0 from the right, I would say you also get positive infinity. And then since your left-sided and your right-sided limits at 0 are both infinity, what's your double-sided limit at 0? I would say it is also infinity. Okay, same example, part C. Let's have you graph f of x equaling 1 over x. Okay, if you plug in 1, you get 1, plug in 2, 1/2, plug in 3, 1/3, 4, 1/4, plug in 1/2, you get 2, plug in 1/3, you get 3, plug in 1/4, you get 4. Okay, plug in the opposites of all of those things. Okay, there we go. So there's a super cute little graph of f of x equaling 1 over x. For part D, let's have you evaluate each limit. Let's do the limit as x approaches 0 from the left of this function. The limit as x approaches 0 from the right of this function. And just the limit as x approaches 0 of this function. Remember, no superscript means a double-sided limit. All right, my friends, go ahead and take a look at that and see what you think. Okay, so limit as x approaches 0 from the left. Your textbook would probably say does not exist, but I'm going to go ahead and say negative infinity. I would like for you to answer that way as well. Limit as x approaches 0 from the right. I would say positive infinity. Your textbook would say does not exist. I'm hoping that you will say positive infinity. Now, what would we say about the double-sided limit at 0? I'm going to repeat something I said earlier. A double-sided limit at a given target number will only exist if the left-sided limit and the right-sided limit both exist, which I would kind of say they do, and they both equal the same thing. So in this case, because they equal two different things, that is when I would say does not exist. And then short for does not exist is DNE. All right, my friends. Example 4. Actually, let's just make this part E. Okay, this should be a little challenge for you, I think. Let's think about what would the limit as x approaches 0. Yeah, let's do limit as x approaches 0. Let's just say from the right of sine of 1 over x. So let's have you think that one out. Okay, so one thing I want to point out is that since the sine function does not have any, itself, it doesn't really have any x terms in it, really we'd apply this limit statement to the 1 over x part. So this would be the same as the sine of the limit as x approaches 0 from the right of 1 over x. And this is the step that I put here is the kind of thing that usually goes on in our heads. It's not something that we usually would write. You could, of course, if you wanted. So really what we're going to do is we're going to figure out what happens when x goes to 0 from the right on this part. And then once we know what happens here, then we'll see what happens if you take the sine of that result. So what do we get here? You could look at this picture right here or look back or whatever. As you plug in numbers that are really close to 0, but from the right side, you're going to get numbers that approach positive infinity. So basically, you're taking the sine of something that is approaching infinity. I don't know why I wrote that in. Okay. So you're taking the sine of something that's approaching infinity. So picture the sine wave, And so what does the sine wave do as it approaches infinity? The sine wave just keeps oscillating between -1 and 1. And so because of that, we would actually say that this limit does not exist because this inside piece approaches infinity and then the sine wave would just keep oscillating between 1 and -1 as its angle approaches infinity. So it doesn't settle. It doesn't settle down and become anything in particular. So we would say that this limit does not exist. Okay. Example 4. Okay. Let's see what happens. Okay. All right. Let's have you evaluate each limit. Part A, the limit as x approaches 2 of 7. Part B, the limit as x approaches 2 of x. Part C, the limit as x approaches 2 of x cubed. Part D, the limit as x approaches 0 of the square root of x. Okay, so go ahead and think those out for yourself, and then we'll just check and see how it went for you. Okay, so this is definitely a time when we overthink things. So in that spirit, I will probably over-explain these. For part A, your graph would have been y equals 7 or f of x equals 7. So your graph would have been a horizontal line where your y coordinates are all 7. And so what happens when you plug in numbers that are infinitely close to 2 from the right and the left? Well, you get numbers that are 7. So we would say the limit as x approaches 2 of 7 is 7. The limit as x approaches 2 of x, if you're thinking graphically, here's y equals x. And then let's say here's 2. So if you plug in numbers that are getting infinitely close to 2 from the right and the left, then from both sides you'd get numbers that are getting infinitely close to 2. Notice that for the last two problems, the limit value is equal to the function value. Like I really just kind of plugged 2 in right there and I got my answer. Well, that's going to be the case when your graph is continuous. So like think about x cubed for a second. The graph of x cubed is continuous everywhere. So that means that in this case, because your graph is continuous everywhere, including 2, I could seriously just plug the 2 in to it and get my answer. So 2 cubed is 8, and so I'm done. Now, would that apply here? Could I say the answer is the square root of 0, which is 0? Could I do that? I think the fact that I just wrote that question mark over that equal sign should tell you probably no. So in this case, think about the graph of the square root function. And so you can see you have an endpoint at 0. So if I had asked you what's the right-sided limit at 0, the answer would have been 0. But if I had said what's the left-sided limit at 0, you would say undefined, which would mean your double-sided limit, in this case, is undefined. There we go. All right, my friends. So and this example is dedicated to the fact that a lot of times you can kind of treat a limit like a double-sided limit, but this part D here shows you why we're a little careful and we think about graphs or tables or something to kind of validate what we've got. Okay. All right. Let's see. The last piece here is not my favorite thing to do because it's just kind of a little dry, but it's properties of limits, and the couple of years that I've tried to skip it, I've been sorry because my poor students would come to me a week before the BC exam and be confused about things that they really shouldn't be confused about. So we're just going to get this done. Okay, so properties of limits. Let's do the limit as x approaches c, where c is a constant here. Let me get some paper to cushion my writing. Where c is a constant of another constant. So think about what do you think we would get there. If you need an illustration for this one, we kind of did one in the previous example when I did the limit as x approaches 2 of 7. See how your target number is a constant like it has here, and then your function rule is a constant as well, and the answer here was 7. So in general, the limit as x approaches a constant of a constant would just be that constant. There you go. So that's property 1. Property 2, the limit as x approaches some target number of a constant being multiplied by a function of x. And an illustration here would be like the limit as x approaches, let's say pi over 3 of like 17 times sine of x. And if you're not sure what this property is going to say, then think about maybe how you would go about something like this. So for me, I would think about the sine wave. The sine wave is continuous everywhere. That includes pi over 3, so I would probably just plug the pi over 3 in. I'd take the sine of pi over 3 and I'd multiply the result by 17. So if you kind of do that little metacognition piece where you think about how you think, really what we did here was we really took the limit as x approaches pi over 3 of this function of x piece, and then we multiplied that answer by that constant there. And basically what this is showing is it makes sense that if you want, you could factor constant multiples in front of limits. So in general, we would say the limit as x approaches c of a constant times f of x is that constant times the limit as x approaches c of the function of x part. Now, question before we move on, would this property have made sense if instead of pulling the constant multiple out front, we pulled the f of x part out front? Would that make sense for like this example? No, it wouldn't. Good, okay. All right. It's so fun teaching all by myself, but pretending you're here. All right, property 3. The limit as x approaches c of one function of x plus another function of x. And so an example there would be like the limit as x approaches 2 of, let's say, x to the 4th plus 1 over x. So in this case, your target number is 2, your first function of x is x to the 4th, your second function of x is 1 over x. So what would you get if you evaluated this? Could you just plug the 2 in? Yes, x to the 4th, continuous everywhere. 1 over x, continuous everywhere but 0, so it's continuous at 2. So you could totally just plug the 2 in. And so you'd plug the 2 in here, you'd get what you get. You'd plug the 2 in here, you'd get what you get. You'd add them together. So really what I'm trying to say is that if you have addition of 2 functions of x, really it makes sense that you could take the limit as x approaches 2 of the first function of x, take the limit as x approaches your target number of your second function of x, and then add the results together. And so the answer either way, either if you had done it as written or if you had distributed the limit over addition, either way, what would you have gotten? 16.5? There we go. And so in general, if you have addition of 2 functions of x inside a limit, you could distribute the limit over addition, which is super special because very few things in math do distribute over addition. There we go. I guess I should go back and evaluate this one up here. So what's the sine of pi over 3? Is that root 3 over 2? So I think you would have gotten 17 root 3 over 2. Yeah. Okay. Let's see. Property number 4. Actually, you know what? Let's save ourselves some writing. What if you are subtracting 2 functions of x? So for example, here, what if you had subtraction? And I hope it makes sense. You could have just distributed the limit over the subtraction. You would have gotten a totally different answer. But that means that if you have a limit and you're distributing it, you could distribute over addition or subtraction. So I'll just use that green pen and show that both of those rules. Okay. Next one, limit as x approaches some target number of one function of x times another one. Go ahead and see what you think that'll be. We'll make a quick illustration for something like that. Let's say we did the limit as x approaches, let's say 11 of x squared times e to the x. Go ahead and see what you'd get for something like that. X squared, e to the x, they're both continuous everywhere, so you could just treat this like a function value. You'd end up with 121 times e to the 11th. Which if you think about what just happened, really what you did was you took the limit as x approaches your target number of your first function of x, and then you multiplied it by the limit as x approaches 11 of your second function of x. If you just slow down and think about what you had done there in your head, then it would make sense that you can distribute limits over multiplication. So the property in general is the limit as x approaches c of f of x times g of x is equivalent to the limit as x approaches c of f of x times the limit as x approaches c of g of x. There we go. One more property, and we are done with this dry part. And then we'll have 2 more examples, and then we'll be done with this lesson. Okay, example 5, let's do the limit as x approaches c. Come on, what do you think it's going to be for? f of x divided by g of x. What could you do there? A demonstration for this could be the limit as x approaches pi of e to the x over cosine of x. So e to the x, cosine of x, both continuous everywhere. So you could totally just plug the pi in. And so you'd plug the pi into the top, you get e to the pi, you plug the pi in the bottom, you'd get -1, and then you'd have your answer. So really, if you think about it, you would take the limit as x approaches pi of the numerator, and you'd divide it by the limit as x approaches pi of the denominator. There we go. So in general, you could take the limit as x approaches c of your numerator and divide it by the limit as x approaches your target number of the denominator. And then this one has a little disclaimer that that works as long as the limit as x approaches c of g of x is anything but, you named it, 0. There you go. All right, my friends, are we on, what example are we actually on? Okay, I think we're on example 6, but you can fix it if this is not example 6. Actually, example 5? Example 5. I think we're on example 5. I don't know. Okay. Example 5, let's have you evaluate each limit. Okay, and we're actually only going to do one of these, and so we're going to do this kind of in a not verified, like a little proof style here. So we're going to have you evaluate each limit using only one property of limits at a time. And not only that, but you know what I need to do? I need to give you the names for the limits, for the properties. So, okay, so the name for this first property, where you take the limit as x approaches c of k and you still have k, the name for that is the limit of a constant is that constant. Property 2, where you can pull the constant multiple in front of the limit and take the limit of the remaining function of x. This is called the constant multiple rule for limits. For limits. Okay. Properties 3, where you can distribute the limit over addition and subtraction of two functions of x. This is called the sum or difference rule for limits. And this property where you can distribute the limit over multiplication between two functions of x. Yep, the product rule for limits. And last one, yep, the quotient rule for limits. Okay, now that you have those written, now when I come back to example 5, the directions are evaluate each limit using only one property of limits at a time, and then you're supposed to state which property you used. Okay. We're only going to do one example like this. It's an exercise. After this, you get to just evaluate the limits in any way you want, and it's okay if all the stuff that we're about to do happens in your head. So, so let me show you what we're going to do here. It's just an exercise. The limit is x approaches 3 of the quantity x squared minus 4x plus 5 times the cosine of pi over x. Okay, now let's say the directions weren't what they are. What if the direction just said evaluate the limit? Well, x squared, continuous everywhere. 4x, continuous everywhere. Pi over x, continuous everywhere but 0, but that's not 0. And then cosine continuous everywhere, and 5, multiplying by 5 doesn't change that. So most of us, and in the future after this example, we're all just going to plug 3 into this sucker. So what would we have? We'd have 9 minus 12, negative 3. So I'm just going to say negative 3 plus 5 times, let's see, cosine of pi over 3. What's cosine of pi over 3? Is it 1/2? So plus 2.5 because you multiplied it by 5. And so we end up with negative 1/2. Okay, from here on out, if you would like to just do that and not show a bunch of steps, then that's fine. But if you're asked, if the directions say this, then you get to slow down and think about all the properties that you could apply. So, okay, so which property would make sense to apply first? I would distribute the limit over the addition and subtraction. So I'd rewrite it as the limit as x approaches 3 of x squared minus the limit as x approaches 3 of 4x plus the limit as x approaches 3 of 5 times cosine of pi x. And what property did I just use? I just used the sum difference property. Okay, next I would use the constant multiple rule with the 4 and the 5. So you'd be left with the limit as x approaches 3 of x squared minus 4 times the limit as x approaches 3 of x plus 5 times the limit as x approaches 3 of cosine of pi over x. Okay, and that is called the constant multiple rule. Okay, and then evaluating each one. There we go. All right, that's just an exercise in metacognition of naming the properties. It is not better to show all those steps than to do it the way we did the first time, but it is some practice with getting used to the different properties and the fact that the order kind of matters. All right, my friends, last example. Okay, directions are for you to evaluate. Part A, let's give you the limit as x approaches infinity of e to the negative x. Part B, let's see, where can I fit this? Part B, let's give you the limit as x approaches 0 from the right of the natural log of x. Part C, limit as x approaches infinity of the natural log of x. Part D, limit as x approaches 1 of the natural log of x. Part E, limit as x approaches 0 of the natural log of x. F, limit as x approaches 0 of cosine of x. G, limit as x approaches infinity of cosine of x. Part H, limit as x approaches 0 from the right. Cosine of 1 over x. All right, my friends. Okay, go ahead and do what you're going to do with those. Remember, this lesson is dedicated to evaluating limits either graphically or numerically, where you do a t-table. And I know I did not do a lot of t-tables. That's because I rarely do. I consider t-tables my kind of my net, like, you know, plan W or something like that. Anyway, but you could always make some t-tables and choose, in this case, x values that are getting really large in magnitude. You know, pick 100, 1,000, 10,000, and plug things in. But I'm going to use this as an opportunity to review these graphs. So e to the negative x, if you were to plug in 1, 0, or negative 1, so like let's plug 0 in, so you'd have e to the 0, which is 1. Let's plug in positive 1, you'd have e to the negative 1, which is about a third. It's like 1 over e. And then if you put in negative 1, you'd have the opposite of negative 1, which is 1, and then you'd have e, which is just shy of 3. That's my poem for the day. E is just shy of 3. There you go. Okay, so here's your graph. And then it's asking what happens as x approaches infinity. So as you plug in these numbers for x that are very increasingly large in magnitude, what y value do you think your graph gets infinitely close to? And I claim that you would get infinitely close to 0. Now, some unnecessary nerdiness that does not make your answer more correct would be to point out that you are approaching 0 from above. So if you ever see that little superscript on the 0, it's just pointing out that you're getting infinitely close to 0, but from above it. Your answer, though, is just 0. Okay. Now for the next one. Notice the next, 4 questions were about the natural log of x. So let's just take a look at the graph of natural log of x. So I guess I'll put that here. So for logarithmic functions, it's best to plug in the base, which natural log of the base is e. So what's the natural log of e? It's 1. It's best to plug in 1 always to a logarithmic function. So natural log of 1 is 0. And 1 over your base, like 1 over e, which is roughly 1/3. Natural log of 1 over e would be negative 1. And so here's a pretty decent little graph of the natural log function. So this, for part B, they're asking what happens as x approaches 0 from the right. So I claim that if you plug in numbers that are getting increasingly close to 0 from the right side, that your graph would shoot down to negative infinity. So I would say negative infinity. Remember the back of the book, they'll say does not exist, but I'm looking for the answer negative infinity. Part C, what about the limit as x approaches infinity of the natural log of x? So you get to go back to the same graph. So what happens if you plug in numbers that are approaching infinity? So you plug in really big x values to natural log. It grows, it continues to grow slowly, but it continues to grow. So since your graph continues increasing, you would say infinity here. The limit is x approaches 1, and this is a double-sided limit. So here's 1. And so if you plug in numbers really close to 1 from the right, you get numbers close to 0. Plug in numbers really close to 1 from the left, you get numbers really close to 0. So I would say the double-sided limit is 0. Part E, limit as x approaches 0 of the natural log of x. So if you approach, this is a double-sided limit. Well, your right-sided limit at 0 is negative infinity, but your left-sided limit doesn't exist. So I would say the answer is does not exist. simply because your left and right-sided limits do not both exist and also do not equal each other. Okay, part F, limit as x approaches 0 of the cosine of x. Well, cosine's continuous everywhere. You could think graphically also if you want, but really you could just plug the 0 in, take the cosine of 0 and get 1. Or you could have been more careful and, looked at the graph. And you could see from the right and the left side, you've got y values that get infinitely close to 1. Limit as x approaches 0 of cosine of x. So a quick sketch. You could see that cosine will just keep alternating between 1 and -1. There's no certain y value that it will attain and flatten out at. And so we would have to say does not exist here, because it doesn't become just a certain y value. And then this is kind of a throwback to earlier. This is limit as x approaches 0 from the right of cosine of 1 over x is the same as cosine of the limit as x approaches 0 from the right of 1 over x. And so this inside part, this would approach infinity. And so really part H was part G in disguise. And so you would say does not exist. Very good. Just wanted to go through that one again with people one more time, just in case it didn't make any sense the first time, and breaking it up into parts helped. All right, my friends, I know this was a long one. Typically, this is something we would have spent 2 class periods on, and we did get it done in just a little over an hour. So anyway, I hope this helps, and I hope everybody's doing great. Take care, everybody.